Okay, thank you. And thank you, Molaei, for your presentation. So we have to continue for another presentation. The title is Automated Value Detection in Piping and Instrumentation Diagrams. The authors, Mohit Gupta, Xiaolin Wei, and Thomas Senarski. Okay, so go ahead. Okay.
Okay. Great. All right. Hello, everyone. I'm Thomas Czerniawski. I'm a new assistant professor at Arizona State University in the US. And there I run the Edifice Lab, where we're automating the creation of digital twins using computer vision. It all starts with reality capture, where we deploy cameras, lasers, drones to create these high fidelity digital representations of the built environment. We then write software to process this visual data into different semantic categories and enrich these 3D models with semantic information to support decision-making during construction, operations, to monitor things like safety and security, evaluate efficiency, track progress, detect defects, guide robotic systems, and support remote presence of expert resources. So this is the group now. Xiaolin Wei presented yesterday on automated wall modeling and 2D drawings. And Mohit Gupta is the first author of the work that I'll be presenting now on automated valve detection in P&ID drawings. So about a year ago, I was sitting down with one of our industry partners, Eric at Sunt, and he was complaining about how much time his construction coordinators were spending on doing takeoffs in P&ID diagrams. So you're given a thick booklet of sheets that look like this, and you have a legend of different valve types. And at the beginning of a project, a person now needs to go through this booklet, identify all of the valve symbols, transfer all of those valves into a spreadsheet so that you can then go and order all of this equipment. The longer this takeoff takes, the more delayed the actual order of the equipment becomes. And if there is a long lead item, that can cause problems. And I'm listening to his complaints and I'm thinking, well, this is something that can be automated using today's technology. And I kind of drew out this conceptual system on the whiteboard. I'm like, well, it'll start with, a neural network that detects symbols in the P&IDs. You also then do some optical character recognition to detect the text. Then you do some kind of spatial association of the text with the valves. And then you have this system output a valve list. And he's like, that would be great. Can we do a pilot? And I said, yeah, let's do it. Let's see what we can do. So our pilot had a limited scope in two ways. So one, we focused exclusively on just the valve detection step. And we also limited the semantic scope just to a single valve type for this proof of concept. The study was made interesting by two challenges. The first was just a ridiculously small data set. For whatever reason, they just refused to give us more data. I kept pushing and pushing, and they said, well, the designers say that the information in these drawings is, our IP, it's super protected, and we just don't feel comfortable releasing this to an academic community that likes to share things. So I'm like, okay, fine, we'll make do with 3 sheets. Not ideal, but we moved ahead anyways. And then the second problem, I'll explain later on, is adversarial symbols. These are symbols that look very similar, but actually represent different types of valves. And we kind of tailored our method to deal with these specifically. So dealing with the first challenge, You can't train a deep neural network with so little data. So we implemented data augmentation to create a large synthetic data set. The first step was to split our 3 sheets into a train and test set. We had 2 sheets for training, 1 sheet for testing. From our 2-sheet training set, we did random cropping. These are taking small windows of 256 by 256 pixels. We took, I think, 1,000 crops. Yeah, that's right. Then we combed through our 2 sheets and we identified all of the instances of our target valve and all its variants. And so now we had our crops. We had our target symbol variants. We took a crop, we selected one of the variants, and then we copied and pasted those valves into the crop. One of the side benefits of using synthetic data is it doesn't actually require any manual annotation, which, as any of you who have been involved in deep learning research know, that creating training data manually is a real pain. So here, because we were just pasting the target symbol into the sample, we had the ground truth bounding boxes just as a byproduct of this process. And so there was no manual annotation required. So now we had our data set and we were ready to train a neural network. The architecture we chose to use was a YOLO V2, which is a standard off-the-shelf detector. We trained it, and these were some of the results. So in our 1-sheet test data set, this is the region where the target symbol can be found. So I'll just zoom in on that. There were 5 ground truth target symbols, and our neural network managed to successfully detect 3 of the 5. And it made 4 errors, 2 false positives and 2 false negatives. And so here we see our second challenge. The first one was the small data set. The second challenge, as you see with the false positives, are these lookalike symbols. They're a different kind of object, looks very similar to the one that you're trying to detect, and it causes the neural network to become confused. How do you overcome this? Obviously, you can get a larger data set, but we took the approach of synthetically creating samples that had both the target symbols as well as the adversarial symbols together. So to do this, we went through our 2 sheets. We looked through all of the different symbols that are present in the sheet. We identified the ones that could be considered these adversarial symbols. And then we went through 20% of our training data. So our entire training set was 1,000 of these crops. So 200 of these samples, we went in and we pasted these adversarial symbols right next to our target symbols. The hypothesis being that if we provide the neural network these really challenging cases during training, it will actually force the neural network to become a more capable differentiator, a discriminator between our target symbols and these lookalike symbols. And our hypothesis was confirmed because after this fine-tuning with these more challenging cases, these were the results where we successfully detected all 5 symbols, and there were no longer false positives or false negatives, which was kind of a surprising byproduct of performing this fine-tuning. So the limitations of this study, we focus on 1 symbol, and so clearly, we don't know how it will perform on other kinds of symbols. We believe that the process is general enough, and because it doesn't require any manual annotation, scaling to more symbols and to different styles of drawings will actually be pretty straightforward. And that's in fact, it's kind of in fact what we're doing now. So we're about to submit a journal article that expands on this work. The extension to this involves creating a general purpose symbol detector that acts as a kind of foundation for performing single shot symbol detection. The prototype that we have allows a user to upload a legend. The legend is processed to identify all of the symbols of interest. We then use the existing model for single shot learning, and it was created using semi-supervised and self-supervised learning methods. So that's the presentation, and I'm happy to take questions if we have time.
Thank you. Jeez, I've just swallowed
Thank you,
the
Thomas.
microphone.
Question?
Yes.
Okay, go ahead.
Yes, sorry. Thank you, Thomas, and very nice presentation. I really enjoyed this. I have two questions. One is about the need. So I can see how if you had old drawings, you would do this. That would be useful. But was this like a new kind of, like you would think these P&ID diagrams, they come from like, I don't know, BIM models or whatever, and therefore, you know, getting the list of valves should be straightforward, you know, not go back to the 2D drawings and try to rediscover them. So I don't know if it was the case in that case, or if they were just old drawings and they didn't have that information. And the second question is there a lot of variability in the appearance of the symbols? So could you just not do some sort of convolution? You know, move the symbol across the image and just convolve it at every pixel location and then look for the spikes.
Sure. So the first question related to need, that was also one of my first questions to the industry partner. I'm like, don't you guys use like smart P&ID software where all of this is digital and you can just do automated takeoffs? And they're like, no, we still get most of our designs in paper format from the designers. So I'm like, well, that sounds like a problem in and of itself. And this is just a Band-Aid on top of a much larger problem. But, you know, I didn't question it too much. I'm just like, these people are dealing with a reality that I'm not familiar with. So, you know, I'm going to take the problem, run with it. It was also quite convenient for me because it was a very nicely sized kind of task for a student that's still learning machine learning. In regards to simpler computer vision methods that would still be performant here, I agree that for this study, we probably could have gotten by with a much simpler algorithm, but we kind of had our mind to the future where we're no longer just dealing with a single type of symbol. We're instead dealing with, you know, what could potentially be hundreds of different kinds of symbols. And this was a data set that came from just a single contractor. But if you look through the drawings coming from different contractors, the actual symbology is quite different, even for the same kind of valve. Like you'll have a ball valve or a globe valve, and this group will have a symbol that looks like this. This group will have a symbol that looks very different. And so when I saw that kind of variation, both in the symbols as well as the styles, I'm just like, yeah, a more traditional computer vision is probably going to hit a wall somewhere in that. And my gut feel was that deep learning would be the only way to go for that kind of general purpose model. Thank you.
Clearly, they need to go talk to their designers and say, can we just get the data straight away? Yeah.
Sorry, any another question? No, in Zoom? Zoom? No, we don't have.